Okay, that's looking very nice. So great. I'll introduce our next speaker for Dask Down Under. This talk is entitled Patterns for Large-Scale Temporal Processing of Geospatial Data Using Dask. Our speaker is Kirill Kouzoubov. And Kirill is a senior software engineer in Geoscience Australia, working on Open Data Cube and managing large collections of raster data. Previously, Kirill worked in computer vision and video compression domains.
All right, can you hear me as well?
Yes, we can.
Excellent, thank you very much for the introduction, and thank you for previous speakers for introducing a lot of concepts that I'll be won't have to introduce myself and just can skip over them. So I work in Geoscience Australia on Digital Earth Australia and Africa. It's the same sort of program that Tisham has described, and we deal with a lot of satellite image data and essentially support remote sensing and data scientists, and making sure that the access to data is active and working well. In this talk, I'll introduce some of the recent achievements, some of the large products we produced for Digital Earth Africa using Sentinel data. And it looks kind of like this. We have managed to process the 4 years, 1 year at a time, worth of Sentinel-2 data for the entire continent of Africa, and computing this J-median result from 500,000 granules from the tiles, the Sentinel calls them granules, and it's a multi-band image and 10 data bands, the 20 and 10 meter resolution bands of the Sentinel satellite, plus the cloud mask band that we need to read. And on the output, we produce the sort of the most typical pixel for every pixel of the continent, as well as the deviation from the typical pixel on the continent. So the large image on the right is the true color thumbnail of a 401 gigapixel image. This is only the RGB bands, but there are more. And the smaller image over here is the median absolute deviation, the false color representation of how much a pixel changes over the year. You can see that the Sahara is kind of black. That's because sand looks very similar in winter, summer, or autumn. But then other areas have pretty colors because there is a significant variation over the year. So some big numbers, you can see this is a significant task to go through that many files. And we processed, like I said, 4 years, 1 year at a time. Obviously, we cannot process the entire image at once, so we need to partition the work first. So the partitioning regime we have chosen is shown here. We basically split up the continent into 4,350 96 kilometer tiles. Why such an odd number, you might ask? Well, that's because we also want to work with Landsat imagery, which is 30 meters, and 96 kilometers fits both 10 and 20 and 30 meter pixels as a whole number. We are using, for those of you in the geospatial domain, using an equal area, global equal area projection, 6933. You might notice that the African continent here looks a little bit different than what you're used to. That's because there is many ways to sort of unwrap the globe onto the flat surface, and the one we chose to do looks like this. Equal area means that every pixel, no matter how far from the equator, is equal area. So that's a property that is not common in the projections that are commonly used. So, but it is very important for statistical analysis type of workflows. What is going on here is we have like 73 observations per annual in most pixels, but some pixels lie in these areas of overlap where the satellite passes over them not every 5 days like normally, but every 2.5 days. So essentially doubles the frequency of observations. So that property of the Sentinel satellite and the fact that the way the input data is gridded and how that overlaps with our output grid results in a very variable workload per tile. And the graph in the left corner demonstrates the distribution of work size per output tile that that we need to deal with. That is actually problematic because you need to basically size your Dask processing nodes to the worst case scenario, the largest number of daily observations and the largest number of input data sets. So that's a challenge. I'll introduce the GeoMedian algorithm briefly, very briefly, on the next slide. But these slides give you further information to look after, to look up. The two papers by Dale Roberts and co-authors introduce the application of that algorithm to the geospatial domain, to remote sensing domain, and why the differencing is an important thing. The library we use for actually computing the GeoMedian is HDStats library, also by Dale Roberts. It is open source. It is available on GitHub, but I must mention that the version that we have used is a closed source version that includes some of the yet unpublished optimizations. And but I'm told it will be open sourced. Those optimizations will be open sourced. The results are going to be exactly identical. It just won't run as fast as it did for us. And finally, Digital Earth Africa GEMAT spec, linked below, is also a very interesting resource, very well done, I thought. And in fact, I stole that picture from there, which describes what the geomedian is, geometric median, is all about. It's essentially kind of like median, but in higher dimensions, right? So we treat every pixel as essentially a point in our case, 10D space. But this graph shows you like an RGB example because it's 3 dimensions is the maximum we can handle as humans. So essentially, given every pixel, given every observation of this pixel throughout the year, we collect them all, and in this 10-dimensional space, we find a location that minimizes the Euclidean distance to all the pixels, to all the observations of the same pixel. So this is very different than if you perform that task individual band at a time, right? Because an average between orange and brown is not the same thing as an average across red, green, blues of the orange and brown. And so this property of combining all the bands turns out very useful for the remote sensing. And that's why we want to compute that rather than a simpler computation like a median of individual bands. It also makes this computation significantly harder. The algorithm that actually finds the geometric median is it's a variant of least squares essentially, and iterative reweighted least squares, my notes say. So it needs, because it's an iterative algorithm, it requires all the data to be present in memory all at once, for a given pixel. And because it treats all the bands together, all the bands need to be present all at once for a given pixel. That makes it need a lot of RAM. And that's a challenge that we have faced and addressed. So before we can compute the geometric median, though, we need to load the data. And that is roughly the data loading pipeline that we have in the system. It's a lot of going on, as you can see. I wonder if I can use the mouse to highlight things. Can people see my mouse?
I can see that. Maybe a bit tricky depending on how large.
Yeah, no, that seems good, Kirill.
All right.
Nice.
Okay, so each individual band and each individual time slice is processed kind of separately. We start off by loading data from a simple storage service on Amazon object block store. We load the data in its native resolution, projection, and everything else native. We then group those granules, those sentinel images that share a common coordinate reference system together and essentially align them to each other and then fuse them. So coordinate reference system, if you're not familiar with geospatial sort of jargon, essentially think of it as if they have the same one, then then the two images can be aligned just by sliding on top of each other, roughly speaking. In case of Sentinel, they can be the sliding increment is a single pixel. So essentially, if you align the two together, the pixel boundary is aligned perfectly. But because the world is a sphere, not all projections sort of apply globally. And the projections that Sentinel is using, the UTM, they kind of come in stripes. So the projection switches over as you move from east to west or west to east. And so those images cannot be aligned together immediately. First, you have to slightly rotate and stretch them before they can be fused, mosaicked into a single raster plane. So this is the reproject plane, reproject box that is happening here. Essentially, we are stretching and twisting the images such that they can be aligned together because we want one single observation for a given day. It just happens to be stored in slightly different projections. So once we have those things aligned, we fuse again. In our case, fusing is basically taking the first pixel that contains data, because in this case, we're processing pixels that are really the same pixels. They've just been chopped up and stored twice, essentially, by the Sentinel processing pipeline. But clouds are always present and in the data, and we need to remove those pixels before we compute before we do any further processing. Geomedian is fairly robust to outliers. So if some clouds get through, it's not too much of a problem. But if every cloud goes through, that's not so good. So to do that, we repeat the same process of loading the data for this band called scene classification layer, which contains essentially it's a categorical data. It's enumerated sort of data that says every pixel of value 4 is a cloud or whatever it is, the number exactly is. So the masking bands go through a similar process, except we have this extra step here, which is called bool in this case, which basically transforms the scene classification layer, which is a bunch of integers, into a Boolean image instead. We're setting pixel to 1 for every pixel we don't want in the final output, because we think it contains the cloud. We then can fuse the areas of overlap with just your simple Boolean OR, because if you want, even though it's the same pixels, the classifications are not always the same, unfortunately, because it's an artifact of the processing system of the Sentinel satellite imagery. And again, we perform the reprojection into the final coordinate reference system of the output and merge it again. And now we have a mask, and then we can apply that mask to the data on each individual band. And essentially, the concept here is we use is no data. Essentially, we assign these images are all integer 16-bit integers, but not the entire range of 16-bit values is used for the data. It is more than 256, though, that your typical image you might be familiar with. And essentially, we mark those pixels that have been classified as cloud as a no data image. So if we only have bands that are in this common, only have one coordinate reference system present, which is common enough, then we can skip the second fusing step and just go directly into the erasing. And this is where Dask really shines, because we can build a simpler graph right away. We don't need to delay this decision making until later. We just delay the actual work. But the graph that comes out, and this is all handled by OpenDataCube and other libraries in this ecosystem, it's all Dask here, right? So this is great. And then we repeat. Then we repeat this process for every time slice that is present and construct this fairly large Dask array and a very large Dask graph. So now we have that. How do we use the data further with an algorithm that is not Dask native? Well, you can start with a very simple approach like this. You just call data.compute, and then you call your algorithm on the result of that. I mean, it's conceptually straightforward. It's great in a way, but it has a bunch of negatives. Primarily, you'll have to pull all this data back to your local machine, right? So that's not ideal, because maybe you're just working on a laptop and you're connecting to a cluster in the cloud that is significantly more capable and has more RAM. You'll need to copy that data across as well, which again is costly. And if you are working on a reasonably sized machine and you have a local installation, you don't have the data transfer costs, but you still have the issues with RAM. Essentially, if you have 10 1 gigabyte slices and you want to put it in a 10 gigabyte slice, which is what .compute does, you need 20 gigabytes worth of RAM for a very brief moment, right? So the memory usage is essentially the available memory you have if you adopt this approach is half is basically halved because of this duplication, because this .compute here collects all the different bits of your input data and then duplicates them in order to give you a consistent view. So what are the options we have? We can do a more Dask native approach to this, right? So rather than bringing the data to the algorithm, we bring the algorithm to the data. So we're using that you can use data map blocks to simply apply the algorithm to the data on the worker, and you send in the computation to the worker rather than the other way around. Because your algorithm needs the entire time dimension to be present, you need to rechunk everything first, right? So that's why this Dask chunk time -1 is there. We're saying that for the time axis, please assemble all the chunks into one single large chunk. So it's better in a way, because the work is done on the worker. You don't need to transfer the data over the network back to your machine. It supports distributed operation. You can have if you have spatial chunks present, then you can have multiple workers doing this thing. But the data transfer internal to the cluster is still a problem, a significant concern, in fact, for problems of our size, at least it is. And the data duplication issue, the RAM halving availability issue is still a problem as well. It's the same issue. You have 10 chunks, you need to put them into one chunk. You need double the memory, right, available. Well, one option is just get more memory, right? But in the cloud, if you want to buy more memory, you have to buy more cores. You have to buy and pay more, right? So you better be also using all these cores efficiently, and that might be hard too. And eventually you reach a point where there is too much RAM. You still need too much RAM. What we found is that this approach is what we adopted first, what we tried first. And you can try to make your chunks spatially smaller, for example, to help with memory usage. And that works, right, somewhat, except it is often difficult to convince the Dask scheduler to not bite more than it can chew. What we found is that it will often try to do more chunks at once than it can fit in memory, right? Because it doesn't really know how much memory it will take, right? It just has some heuristics about in what order to evaluate things. So we still pushed on with that approach for a while. We tried to manually persist individual chunks of an image, so that, well, in our case, we reduced the output is about 70 times smaller than input, right? So if we persist, so that this Dask persist operation, it will load the entire column of data, run the G-median on it, and now we have 1/70th of the data, and all the input data can be then released. That approach worked for us, but it made the Dask graph kind of discontinuous. We had to stop. We say, okay, we built an input graph. Now we have to introduce this manual guiding of the Dask evaluation with persist and waiting for persist to finish, and then resume the evaluation of the rest of the result that would save the results to disk or to object store. So that was not super efficient in that regard. But also, the smaller you make your spatial chunks, the more you pay per pixel, right? An obvious example, if you were to read one single pixel at a time, that would be really costly per pixel, because pixels are not stored one at a time. They're stored in blocks of 512 by 512. So reading millions of pixels is roughly the same cost as reading one. So how can we avoid the rechunking costs, right? Well, one option is by construction, right? If you build your graph such that you store your data, like I think Drago did, in a way that you access the data, then you can assign chunks that at the time of data loading, or even at the time of data generation, such that your access pattern, your storage patterns align, right? But that's only an option if you can afford to duplicate the data. It's a good option if you can afford it. We cannot afford it, right? The Sentinel archive is huge. It's natively coming in as individual time slices, and it's not something we can afford. But what if we can do this instead? What if we could actually place the data we want into the location we need? And by the way, in our case, we're not just rechunking the data. We also need to transpose it. We need to place the temporal dimension as the last one there. So turns out you can do this exactly. What we essentially implemented is the trick we used is essentially to use data array store operation to store the data into RAM, and then essentially wait until everything is finished and then read it back from RAM, but this time with different chunking regime. The chunking regime that puts all the bands and all the time slices into one big chunk, and we create smaller chunks along the spatial dimensions. Now that the data operation is cheap, and so we get a lot of parallelism back to process those columns of temporal data with the G-median algorithm. So what what we gain with this approach. So work is done on the worker, not on the client machine, which is nice. There is no overhead for the data transfer with respect to pulling it back to the processing node or to the controlling node, or no overhead in terms of rechunking either, right? Because rechunking operation usually generates quite a bit of crosstalk between the workers. The memory requirement is halved because we're storing directly into the. We don't need to keep around the temporaries in order to then reconstruct it into one big chunk. And it also had the effect of significantly more predictable scheduling. We would get a scheduler doing the same thing each time, every time, and doing the right thing for us, which is to process every time slice till the end before moving on to the next one concurrently. The major limitation here is, however, is that the task has to be pinned to a single worker, right? Because what we're populating is an in-memory data array, and that in-memory data array exists only on one of the workers. But in our case, that was fine because we actually wanted to use one single worker internally. And if you do have a properly distributed cluster, that's still possible with extra engineering. You just have to tell Dask that that the data store operations can only happen on a certain worker that contains the memory. And yeah, that really helped us. And questions?
Great talk. Thank you very much, Kirill. We do actually have quite a few questions in the chat already, and a few different compliments. So maybe we'll start with the last question we have here from Nick Mortimer. Nick would like to know, can chunks be hidden in a delayed object using the metadata so that the task graph doesn't explode?
Can chunks, sorry, I'm trying to figure out where the chat is. Yeah, can chunks be hidden in delayed object using? We have not tried growing we're using a very simple approach where we build a Dask graph first and then we just evaluate it, the entire lot, right? We have not tried building the Dask graph incrementally on the worker. That is definitely something I do want to look at, but no, we're using a very simple approach of constructing the Dask up front and then evaluating the entire lot. Is that roughly?
I hope so. Maybe Nick can add something extra to the chat if you would like any clarification. We have a question, just a request from one of our attendees. Could you copy paste like the links that you have in this slide just into the chat for everybody?
Yep, we'll do that.
Lovely. And I just want to say that I've noticed not a question, but a really nice compliment here as you've been chatting. When we get to your section on how we can avoid rechunking, Rob Woodstock says, that's just plain clever. I bow to thee, I'm not worthy to be in thy presence. Slightly over the top, but yeah, that's a really nice thing to see. So I think you're teaching a lot of people some fun tricks.
Yeah, thank you. I mean, yeah, it was surprising that to discover that. I thought like surely it would have been done by somebody. Maybe it is. Maybe it has.
And just while you're posting those links in the chat, we have another question. And that question is, can you provide some ballpark range for the cost?
Yes. Well, if you don't make networking mistakes, we ended up spending something like I think it was $2 or $3 US per year. But we did make some networking mistakes, unfortunately, and that ended up being significantly more. But yeah, and this is Africa. This is 4 times larger than Australia, yeah, so it's expensive, but it's not it's not infinitely expensive.
Okay, that's great. Yeah, well, thank you very much, Kirill. I'd like to invite everybody to thank our speaker once again. It was a great talk.